Steel bar cutting involves measuring and slicing steel rods precisely to required lengths using automated cutting machines for uniformity and accuracy. The steel bar heading process shapes the ends of cut bars by forming heads, enhancing bonding and anchorage within the concrete. Coiling the wire around the steel bar involves tightly wrapping high-strength steel wire helically along the length of the pre-cut and headed steel bar. This process enhances the structural integrity and tensile strength of the bar, helping it withstand internal stresses during concrete curing and in-service loading. The wire is uniformly coiled using specialized machines to ensure consistency and precision. The coiled steel bars are transferred to the case and shoe assembly section, where they're placed into cylindrical molds with base shoes. The assembled mold is moved to the concrete input area, where it's prepared for the pouring of high-strength concrete mixture. High-strength concrete is carefully poured into the prepared mold. After pouring the high-strength concrete, the mold is covered to secure the mixture, preventing contamination and ensuring proper curing. This also helps maintain the correct temperature for optimal concrete hardening. Once the case is covered, it is transferred to the bond tightening section, where specialized equipment secures the mold with bolts to maintain internal pressure and alignment during the curing process. In the bolt tightening part, bolts are securely fastened to lock the mold components together, ensuring stability during tensioning and curing processes. The mold with the secured bolts is transferred to the steel bar tensioning section, where hydraulic equipment applies stress to the steel bars for pre-stressing. Steel bar tensioning involves applying hydraulic pressure to stretch the steel bars, creating internal stress. This pre-stressing enhances the bar's ability to withstand heavy loads and ensures optimal performance in the finished pile. After steel bar tensioning, the mold is transferred to the rotary molding section. Here, the mold is rotated to evenly distribute and compact the high-strength concrete around the pre-stressed bars. The rotation ensures thorough mixing, eliminates air pockets, and maximizes the concrete's density. This process guarantees uniformity and increases the pile's strength and durability. Once molded, the pile is transferred to the steam chamber, where it undergoes controlled high-temperature curing to accelerate concrete hardening. In the steam chamber, the pile is subjected to high temperature and humidity for 12 hours, accelerating the curing process and enhancing concrete strength. After curing, the pile is carefully transferred to the demolding part, where the hardened mold is removed, preparing the pile for further processing. Demolding the case is the final step in the PHC pile production process. Once the concrete has cured in the steam chamber, the pile is moved to the demolding area. Here, the hardened concrete is carefully removed from the steel mold. Specialized machinery or manual labor is used to strip away the casing without damaging the pile. This process reveals the fully formed, high-strength concrete pile with a smooth surface, ready for inspection. Removing the mold allows for any adjustments or finishing touches before the pile is moved for further quality checks or ready for transportation to the construction site. After demolding, the pre-tension bolts, which were used to secure the mold during the tensioning process, are carefully removed. This is done to release the internal pressure and allow the steel bars to fully stabilize, ensuring the pile's structural integrity. The process starts with 3D bending machines, precisely shaping steel wires into specific configurations required for structural support. These shaped wires are then used to fabricate wire mesh and rebar cages, which provide strength and stability to the sandwich wall panels. Mold assembly involves setting up steel molds to define the panel's shape and dimensions. These molds are then thoroughly cleaned and coated with release oil to prevent concrete adhesion. Next, the external skin wire mesh is carefully placed inside the mold, followed by securing the fixed wire mesh. Simultaneously, the concrete batching plant mixes high-quality concrete, which is transported via shuttle systems to ensure timely and efficient pouring into the molds. The first concrete casting involves pouring a precise layer of concrete over the external mesh to form the panel's outer skin. After the first concrete layer sets, insulation material is carefully placed to form the thermal core between the concrete layers. Internal skin reinforcement installation involves placing steel mesh and rebar over the insulation to strengthen the panel's inner concrete layer. The second concrete casting covers the internal reinforcement and insulation, completing the sandwich structure with a solid inner concrete layer. Surface finishing smooths and levels the panel for uniform appearance. A curing sheet is applied to retain moisture for proper hardening. After covering with a curing sheet, the panels are transferred to a curing chamber. This controlled environment maintains optimal temperature and humidity, allowing the concrete to cure slowly and uniformly, ensuring maximum strength, durability, and long-term performance of the panels. Demolding involves carefully removing the cured concrete panels from the molds once they have fully hardened. This process requires precision to prevent damage, ensuring the panels retain their shape and structural integrity. Tilting is the final step where the cured concrete panels are carefully tilted from a horizontal to a vertical position. This process facilitates their transportation and installation, ensuring alignment and stability during handling. The process begins with the fabrication of a reinforcement cage. This is accomplished using a cage welding machine. Steel rods are automatically arranged and welded into a cylindrical cage structure. This steel cage acts as the internal skeleton of the cement pipe, providing tensile strength and resistance against cracking under pressure. Once the cage is ready, the mold, which shapes the external form of the pipe, is positioned into a hole or a pre-designed cavity in the ground or a machine base. This hole provides stability during the formation of the pipe and makes it easier to work around the mold. With the mold in place, the steel cage is gently lowered into it. Care is taken to center the cage within the mold so that the concrete will evenly encase the steel structure. The alignment must be precise to ensure the structural integrity of the finished pipe. At this stage, the steel cage is fully positioned inside the mold. Next, the concrete mix is prepared and poured into the mold. The concrete must be of high quality and mixed to the correct consistency. As the concrete is being fed, a core vibrator is used simultaneously. The vibration helps compact the concrete by removing air bubbles and ensuring the mix settles evenly around the steel cage. Once the concrete is in place, the upper part of the mold, or the pressing head, is fixed onto the mold setup. This not only seals the mold but also prepares it for the final forming process. The alignment and secure fixing of the mold are checked before proceeding. With the mold fixed, pressing and vibration are applied simultaneously. This step compacts the concrete further and shapes it according to the inner and outer contours of the mold. The pressing head pushes down while the vibrator ensures maximum consolidation of the mix, forming a strong and uniform cement pipe. After sufficient compaction and shaping, the pressing head is carefully removed. This signals the completion of the forming process. The mold, now containing the freshly formed pipe, is lifted out of the hole. This is usually done using a crane or mechanical lifter to avoid disturbing the concrete structure. The mold is then completely removed from the production pit or base and placed in a designated area for the next step. Care is taken to handle it gently to avoid cracking or deforming the uncured pipe inside. After the initial setting period, when the concrete has gained sufficient strength, typically through air curing or accelerated steam curing, the demolding process begins. The mold is carefully opened to release the newly formed cement pipe. This step must be done with precision to prevent chipping or damaging the pipe, especially around the edges. Hydraulic or mechanical equipment is often used to ensure smooth separation between the mold and the concrete. Once removed, the pipe is transferred to a curing area, where it undergoes final curing to achieve full strength and durability. Meanwhile, the mold is thoroughly cleaned to remove any residual concrete, inspected for wear or damage, and lubricated if necessary. This ensures the mold remains in optimal condition for repeated use. By maintaining a clean and functional mold, manufacturers can ensure consistent pipe quality, reduce production downtime, and extend the lifespan of the equipment. The Brighton 1360 sewer diversion project was a crucial part of the construction of the iconic Brighton 1360 Tower, a landmark observation tower located on the site of the old Brighton West Pier. The project involved significant engineering challenges, not the least of which was the need to divert an old Victorian brick sewer that ran directly through the planned location for the tower's foundations. This sewer diversion, completed in January 2015, played an essential role in ensuring the safe and effective construction of the I-360 Tower, which now stands as a stunning modern structure on the seafront. The original sewer, a Victorian-era brick structure, ran along the seafront, passing through the exact area where the new tower was to be built. As the tower's foundation required deep excavation and extensive structural work, the sewer needed to be diverted to avoid any disruption to the existing infrastructure. The challenge was particularly complex due to the location of the sewer directly under what would become a critical part of the tower's vast base. The existing sewer could not simply be left in place, as it would interfere with the massive concrete foundations that were required for the I-360 Tower. To facilitate the diversion, a team from C.J. Thorne and Company Limited, a specialist contractor based in Uckfield, East Sussex, was engaged. This experienced team was tasked with cutting into the old Victorian sewer and redirecting the flow into a new, larger 1,600mm concrete sewer pipe. The work involved careful excavation, precise cutting, and the installation of new infrastructure to ensure that the sewer could be safely rerouted without causing any disruption to the service or surrounding areas. The new sewer pipe was designed to run to the south of the tower's foundations, effectively bypassing the area that would otherwise be impacted by the construction. The concrete pipe was a significant upgrade from the original Victorian brick structure, which was no longer suitable for the modern needs of the city and the increased pressure on Brighton's sewer system. The 1,600mm diameter concrete sewer pipe ensured that the diverted flow could be handled with ease, providing a long-term solution for both the I-360 project and the local infrastructure. The work was not without its challenges. The construction site, located on the busy Brighton seafront, required careful planning to ensure that the diversion work did not interfere with the daily activities of the area or disrupt the public in any significant way. In addition, the team had to work with a range of complex logistics, including coordinating with other contractors and city services, all while adhering to strict environmental and safety regulations. Despite these challenges, the diversion was successfully completed in January 2015, allowing the construction of the Brighton 1360 Tower to continue on schedule. The I-360 Tower, designed by the architectural firm Marks Barfield, was officially opened to the public in August 2016. The tower stands 162 meters tall and offers spectacular panoramic views of the city, the coastline, and the surrounding areas, making it one of Brighton's most popular tourist attractions. The sewer diversion project is a testament to the careful planning, expert engineering, and teamwork required to complete such a complex infrastructure task. The successful rerouting of the sewer ensured that the I-360 tower could be constructed without any delays or unforeseen issues. Today, the project serves as an example of how modern engineering techniques can work in harmony with historical infrastructure, ensuring that new developments can coexist with the needs of a growing city. In the gas industry, one of the most critical and technically demanding tasks is conducting maintenance and connection work on live high-pressure gas pipelines. These operations must be performed in strict accordance with national safety and engineering standards to ensure reliability, environmental protection, and uninterrupted gas supply. A common technique used for such operations is hot tapping, which allows engineers to tap into or modify a pipeline without shutting down the gas flow. This process is particularly valuable when connecting new infrastructure, such as gas distribution stations, or replacing aging components in the system. It eliminates the need for costly service interruptions and ensures that customers continue to receive an uninterrupted gas supply. The video referenced in the document illustrates the connection of a newly constructed gas distribution station, GRPB, to an existing high-pressure pipeline. The new station has a throughput of 45,000 cubic meters per hour, significantly more than the older one it replaces, which had a capacity of 24,000 cubic meters per hour. The connection involves tying in a new DN 426 mm diameter gas pipeline to the existing DN 400 pipeline operating at a pressure of 1.2 megapascals, MPa. The process begins with preparing both the new and existing pipelines. The end of the new pipeline is trimmed and cleaned to prepare it for welding. Simultaneously, the insulation on the existing pipeline is removed at the location where the connection will be made. This area is then cleaned and prepared for the installation of a split tee and a purge fitting. The split tee, which is a two-piece welded fitting, is used to reinforce the existing pipe and serve as the access point for tapping into it. Next, the purge fitting and split tee are welded onto the prepared section of the pipeline. These fittings include both internal and external plugs to manage gas pressure and prevent leakage during the tapping process. A flange adapter is then installed to transition between the split tee and the valve system. A DN 500 shutoff valve is mounted, which will later control the gas flow through the new connection. With everything in place, the purge fitting is drilled first to allow for safe pressure equalization. Using high-pressure hoses, the pressure within the drilling machine is balanced with the pipeline's internal pressure. This is a crucial step to prevent sudden gas release. After equalizing the pressure, the main tap into the pipeline is performed using the DN 500 drilling machine. Once the hot tap is completed, the drilling machines are dismantled. Internal plugs are installed into the split tee to isolate the newly created opening. These plugs are inserted using the valve system to ensure safety. Following this, the shutoff valve and flange adapter are removed, and an external plug is welded into place to fully seal the connection point. The final step is to apply insulation over the entire assembly, protecting it from external environmental factors and ensuring long-term operational integrity. Benefits and applications. This method of hot tapping under pressure offers several advantages. No interruption of gas service, reduced operational downtime, enhanced safety and reliability compliance with industry standards. Such techniques are essential in modern gas distribution, especially in urban areas and industrial zones where shutting down pipelines is not feasible. By using advanced tools and following strict protocols, maintenance and expansion of gas infrastructure can be carried out efficiently and safely. The use of domestically manufactured equipment, as demonstrated in the video by the Russian company Stoptron, also showcases the growing capabilities of local industries in supporting critical infrastructure projects. Hot tapping is a critical process in pipeline maintenance and modification, allowing new connections or repairs to be made without interrupting the flow of gas or depressurizing the system. Ravetti SRL, a global leader in pipeline technologies, offers advanced non-shutdown solutions specifically designed for gas networks, enabling operators to maintain continuous service during essential infrastructure interventions. The core advantage of Ravetti's hot tapping technology lies in its ability to work on live pipelines, even those under full operational pressure. This is achieved through a technologically advanced system that ensures maximum safety and reliability. Ravetti's equipment is engineered for precise execution, allowing for the installation of branches, bypasses, or replacement of pipe sections without compromising the integrity of the network. Ravetti's hot tapping procedure begins with the installation of a specially designed tapping saddle or fitting onto the pipeline. Once secured and sealed, the tapping machine, equipped with a cutting tool, is mounted and begins to drill into the pressurized pipe. The innovative design of the equipment ensures that the medium inside, whether natural gas or other compressed gases, remains contained throughout the process. The cut material, commonly referred to as the coupon, is retained safely, and the tapping is completed without leakage or pressure drop. A major highlight of Ravetti's system is its capability for line stopping, a method that temporarily blocks the flow of gas in a specific section of the pipeline, enabling more extensive maintenance or pipeline section replacement without impacting the overall network. This method uses inflatable or mechanical plugs inserted through a hot tap opening, effectively isolating the work area. What distinguishes Ravetti's technology from other solutions is the high level of customization and modularity. The equipment can be adapted for different pipeline diameters, pressures, and materials, making it suitable for a wide range of gas distribution and transmission applications. Moreover, the entire process adheres to the highest international safety standards, reducing the risk to personnel and the environment.